Okay, works. Perfect. Okay, hello everyone. So I introduced myself before. I'm Simone Bacchio, and today we'll cover part of this training event. I will start with an introduction to high-performance computing, and then it will follow an introduction to Python and mostly the usage of Python in HPC. So let's say a few more words about high-performance computing and understand how it works, what is the purpose of these machines, and how we should use them. So today, in this introduction, we will see an overview of what are the supercomputers in Europe nowadays in the future. We will have a look to the top 500 list, which is the list collecting the largest 500 supercomputers in the world, ranking them and presenting various information in a very nice format. Then we will talk about the difference between CPU and GPUs and parallel programming. Okay, so before starting, let's try to understand what is the difference between a supercomputer or in general a computing node against to what every one of us has, which is a desktop or a laptop. So what do we have usually in a desktop or a laptop? Well, we have a CPU. This is the one processing unit that does most of the calculation we need to. Then we have RAMs, DDRs, memories, where the data are stored during runtime and processed. Many devices may have also GPU, which is a graphic processing unit, and is specialized for, as the name says, for graphics, but nowadays it's very important also for calculation on data. And then we will have also some power supply, and we will have some memory storage, some SSDs or hard drives. On the other hand, a computing node, it's one of these slots here. This is one of the major component of a supercomputer. What does it have? Well, it has much larger CPUs, in this case are 2 in the same node. So usually they may reach 64 cores against 8 cores of your laptop commonly. So these are 64 cores. They have much more memories. You can see here all the slots. Usually it can reach up to 512 gigabytes per node, which is a lot compared to, I don't know, 16 or 32 gigabytes in your laptop. It does not have 1 GPU, but it has 3, but actually this node has 6. There are other 3 under. So it may have 6 GPUs in one node. And on the other hand, does not have a hard drive, no voltage converter, because everything then is centralized. So what you want to do is to use all this huge computing power. This is a huge amount of computing power that you have in one node in the most efficient way for doing your calculation. So you understand that already one node performs almost like 6 of these desktops put together. But in a supercomputer, you don't have one. You have many of them. You have all of these put in a rack. And then many of these racks make a supercomputer. And so like I said, you see, when things start to become complicated, you see a setup of a supercomputer has all these cables, etc. Because what you want to do is not to use one of these nodes, but to use many of them at the same time. So you need to be very efficient in sending data between different nodes, communicating. So very important in a supercomputer is the network. Of course, you want all these nodes to access the same data. So the data is not stored at the level of the node, but it's centralized in very huge storages, which have order of hundreds of terabytes, and archives can reach petabytes. And as well, for efficiency purpose, the power supply and the cooling is everything centralized. So these machines are optimized for performance and for producing results. In Europe, we have many of these systems. Here I have a collection of the largest. So currently the largest supercomputer in Europe is Lumi in Finland. This is, we will see now, it ranks 3rd worldwide. Then we have many others that are previous models. So Lumi is the latest one that came about. There are many computers in Germany, like Jewels, Oak, SuperMUC. There are in Italy at Cineca. There are in Spain, in Barcelona, in France, in Switzerland. These are the largest. There are many other countries that have smaller systems. And these are all systems that you can access for your research. So you can write a proposal and access them and use them for your research remotely. So you are here, you sit here, you connect remotely to this system, and you submit your jobs and use them. And of course, we have also our own small supercomputer here in Cyprus, where we have, for instance, Cyclamen. You see, we have only one rack with 18 nodes between CPU and GPUs, while you understand these systems are huge, have many of these racks, and they are very big. But having a local supercomputer is very useful for test with the latest system. So that's always our goal, to provide, to try to follow up the trends and provide also locally the same hardware that you have abroad. It's very useful to test your code, prepare yourself for then running abroad on the other system. So that's why, even if small, it's very useful to support the local community. So I mentioned before, we are going to look at the top 500 list. Top 500, like in the name, collects the largest 500 supercomputers in the world. This is a list that is active since 1993, and it's collecting since then what are the systems worldwide. These can be any kind of system used for research, academic purpose, industry, and you can see how incredible has been the progress since then. So in this plot, you cannot read well here. On this scale, yeah, here in the slides are slightly cut. So maybe I go out with the presentation. So on this scale, we have the number of flops, and we can go from gigaflops. So giga is the it's an order of magnitude in the measurements that I guess all of you know. So you have gigabytes. Giga are thousands of mega, and then after giga you have teras. Teras are thousands of gigas. After tera you have petas, that are thousands of teras, and then you have exa, that are thousands of peta. So this scale, every line, it's an order of magnitude. So we start from 1 gigaflop and we arrive to 1 exaflop. You can see that the number one supercomputer back in the days was about 60 gigabytes, 60 gigaflops. Yeah, sorry, I forgot to mention. What are flops? Flops are the floating point operation per second. So this is what we use in HPC to measure the power of supercomputer. Like you measure the data in gigabytes, how many bytes you can store. Flops indicates how many floating point operations, so the multiplication between two numbers, basically, or the addition, so the operation between two floating points, you can do per second. And okay, this is measuring double precision, so with standard double numbers. And so 1 gigaflop means that you can do 1 billion of these floating point operation per second. Okay, and exaflops are yeah, billions of billions. So the back in the days was were 60 gigaflops, and nowadays finally we reach what is known as the exascale performance, where the largest supercomputer has performs with 1 exaflop. So this is a big number. I will stress more about why this is very important. So this is number 1, this is number 500. You can see that the number 1 doesn't grow smoothly, does these plateaus here. This is because at some point someone built the largest supercomputer, and then this stays the first one for many months or years. So this is comes out every 6 months, and you can see that the first one, was this system for almost 3 years here. And this happens, while the last one, instead, there are many others, they drop out very fast, and so this grows more linearly, in the same way of the sum. And what do we learn from this linear growth? We learn what is known as the Moore's law, which was stating that the power of this system will double almost every year. So this was the, so every year we would have a system that would perform twice as the previous year. And this was a law that has been followed quite very well until 2013. And then you see that there has been a changing slope, but still it's an exponential growth, but with another slope that does not follow anymore the Moore's law. It's about 1.5. And I will tell you more about this kind of why this changed. So why there has been this change of trend? Basically, this is due about limitation in the manufacturing of hardware, of microprocessor. And what people did up to since the beginning of age of computers, so from the 70s, basically what people did to increase the computing power was to put more hardware inside the processor and be able to do more calculation together. So this was done by increasing the number of transistors and by increasing the frequency and by increasing the single thread performance. And you can see that all these trends together allowed for what we saw before as the Moore's law. But then hardware limitation came about, and for instance, the frequency for physical reason cannot be increased larger than 1 gigahertz, about let's say order of 5 gigahertz. So it's very difficult to increase the frequency further. This is because then the hardware becomes unreliable. Too many errors will come about, and for this reason, there has been a significant slowdown of the increasing performance. So basically, of course, if you can make things go faster, this will produce more calculation per second, but you cannot do it anymore. And what people started then investing on is on the number of logical cores per process. So this is something that nowadays you are all very familiar with. You know that your CPU has many cores and you can do multitasking and run things in parallel. But this wasn't very true up to the 2005, where everything was done by a single core because you were able actually to increase the performance. Since then, instead, the number of cores started this increasing in frequency. It couldn't happen anymore, and therefore one started increasing number of cores. So how many things you can do in parallel, and nowadays parallelism is very important. So I wanted to stress more about exascale. Exascale is this term that is around in HPC since 2008. And there was people since 2008 started thinking about what we could do with exascale system because it would be so powerful. And at that moment, people predicted the appearance of exascale system in 2015. And then you can see that following the Moore's law, this is somewhere where this would happen. But yes, due to the change in performance, this has been very, very hard to achieve. And actually, until nowadays, finally in 2020, in the last release of this list, we had the first exascale system, and it's something that has been very, very a challenge to achieve, and it required a lot of improvement in how supercomputers were built. So let's have a deeper look in how these systems are built and what are their specifications. First of all, let's see what is the European perspective from on this reaching exascale performance. Stelio mentioned the EuroCC project. It is the project that is funding the next generation of supercomputers in Europe. So it has already funded the creation of 5 new petaflops machines. These are available in Bulgaria, Czech Republic, Luxembourg, Slovenia, and Portugal. And the creation of 3 exascale systems that are the largest nowadays in Europe, which is Lumi, that I mentioned in Finland, and Leonardo and Mare Nostrum in Italy and Spain, respectively, that still have to come online, but are being built right now. So these are systems that have order of 200 petaflops per petaflops of performance. Upcoming are ESGAS system. So these are still upcoming in Europe, but I mentioned to you that we already have one, and this is indeed in the United States. This system is Frontier, that is in United States at Oak Ridge, and you can see here the size of this system. So Frontier is a system that has 1.1 exaflops of performance, and it has 8,700,000 cores. So these are the numbers of cores you can use. And it's double the size of the previous largest that was Fugaku. So this kind of, I will not go through all the details on this table, but just to give you an idea, these are the top 5. So we have 3 systems in the USA, 1 in Japan, and 1 in Europe, in Finland. You can see how the numbers can change very drastically from the first to the 5th. So we go from 1 exaflop to half to 150 that is Lumi and petaflops. And the same size is Summit, and also this is about 100. So you see that there is a big difference between the various systems. And these are the number of cores, and here is the power supply. It's a topic that I didn't mention yet, but you can, these systems that are so big consume a lot of electricity. And for instance, the first one consume about 21 megawatt of electricity per hour. So this is the kind of the electricity of a small tower. So it's they are really powerful, but also very demanding. Okay, this is the top 5 in Europe. This is the top, top 5 worldwide. This is the top 5 in Europe. So you can see that we classify kind of between 3rd position, 10th, and 20th. There is, again, a big difference between the various systems. And these, mostly the European system that you could use in your research. So what almost all these systems have in common? The thing that most of them have in common is the hardware. So there is a very big difference in performance, but it's just the size, is how much money they put in. But at level of hardware, they're all the same, almost all the same. And what can you see in this table? You see that many of them have NVIDIA GPUs, different models, but NVIDIA GPUs, or the AMD GPUs, but all of them, apart Fugaku, that was CPU only, have GPUs. And the GPUs are indeed the one that provide power to this system, and is the one that you really need to learn how to use nowadays in order to be able to exploit this system. So unless you have a code that runs on GPUs, it's very difficult to then get access to this system. Unfortunately, it's not the topic of this training event to learn about GPU programming. This will be for the next event. But it's something that, yes, it's the next step you need to achieve with your code if you want to be able to scale on these systems. So, okay, before moving on and talking about CPU and GPU, just a look about future systems. We are going to have in Europe an exascale system, Jupiter, in AGS in Germany. So this is going to come about in 2024. So in a couple of years, we are going to have also our first exascale system. And we have the 2-1 that I mentioned in Spain and Italy. In the same way, though, in a couple of years as well, US will already have about 2 exascales system, which is a Cap10 in USA. So it's always difficult to stay up to pace. So the hardware. The hardware, you can see in this table some statistics about the hardware of the system. Most of them are using Intel for the CPUs. Intel has actually dominated the market since 2000 in HPC, and the only kind of competitor is AMD, and which is again gaining more drafting these days. And the same is true for GPUs, where you can see that the market has been dominated by NVIDIA for many years, for almost a decade now. And we mentioned that many new systems are actual one AMD GPUs, but this is true only since the latest generation, where there are some AMD GPUs also yet. I know for you, maybe are just names between NVIDIA and AMD, but actually are very important information to know, because a code that runs on NVIDIA GPUs will not run on AMD GPUs. So you have to start, you have either to rewrite the code or write it in a portable manner in order to be able to use it on both architecture. So it's also knowing the architecture is very important for being able to use the system. Okay. I said, I mentioned many times now CPU and GPUs. I think as well, all of you already knew these terms, but it's important to understand what are the main differences and why GPUs had changed the way we do computing and we do high performance computing. So what is the main difference between the two systems? Okay, the CPU, we know it's just a processing unit and nothing more. It has, it's only the microprocessor. Instead, the GPU, it's always a separate element in our computer, and it's actually much more than only a microprocessor. So this is actually the microprocessor in the GPU, but it has much more hardware on it. So actually, it's a kind of computer by its own, because it has its own memory storage and other hardware for managing the data throughput. So the GPU is already more than just a processor. And what do they do well? On one side, the CPU is meant for optimized low latency access to data, and it's very fast in doing many different operations, but in a sequence. So for that, the CPU is very, very fast, and indeed, it's where it's the only place where your operative system can run. So your operative system is doing many things together, and it can do it only on a CPU. You will never have an operative system running on a GPU. This is because the GPU instead is optimized for data parallel throughput computation. So what the GPU does, and this is very good for graphics, it processes a bunch of data all together, all at once, at the same time. So it doesn't have 4 cores like here, but it has thousands of them. And they're very small, they do very few operations, but they are able to process a bunch of data all together. So for this reason, it's very good for graphics. You have an image, you just process the image, and you can do transformation of the image. But it's also very good for data science, scientific computing, because nowadays what we are doing, all of us, it's mostly almost linear algebra. We take matrices, we take arrays, multiply them, sum them, and they're all operations that you can very easily do them parallel, and the GPU is great for that. So NVIDIA has shown this trend first, and indeed has invested a lot on producing GPUs that are dedicated for data science. These are different than GPUs for video games, because they have much more logic that is meant for operating vectors, matrices, arrays, etc. So are different kind of GPUs that optimize for data science, and they are very, very good at what they do, and they're very fast. And this indeed has changed the way we do high-performance computing. The high-performance computing moved from the CPU to the GPU. And the trend nowadays indeed are kind of similar. So newer CPU, like we know, they have much more cores. They're much more meant for parallelism, so they're becoming more like a GPU. And newer GPU for data science have a better logic, and so also then they're kind of going more like a CPU. But they're still two very different pieces of hardware, especially in the fact that the GPU is also very fast in what it does, because it has an optimized memory that is much smaller. Here I mentioned you can reach 512 gigabytes. This guy usually it's up to 16 gigabytes. Only nowadays there are GPUs that have more, but it's very fast and directly connecting the hardware to the chip. So these pieces of hardware here are what is named VRAM, and they're directly connected to the hardware. So they are very, very fast in moving data around, process them, and producing. So why the architecture is so important? So once, until we didn't have GPUs, we had only CPUs, you didn't have to worry much about how you write your software, because you will write your code. So you write, how does it work usually, this flow? You write a piece of software, some code, then you ask, this is done in a certain programming language. I guess many of you, I don't know, are familiar with Python. Python, it's not really a compiled code, so it's not good for this example. But if worldview is using C, C++, Fortran, these are compiled code. And so you write your code, and then you ask a compiler to translate what you did in machine code. And so the compiler knows what is your hardware, knows what your hardware can do, and produces machine code for that hardware. So you don't have to worry if you have an Intel CPU, an AMD CPU, an IBM CPU. The compilers will think about that. And we produce that up machine code based on the programming language. But if you have something like a GPU now, or a different kind of CPUs, it's very important. Now, this is going to affect not just how the compiler will do, but also how you write your software, because now you need to write software that is much more meant for data parallelism. And it needs to use the hardware in the appropriate way. So what a computational scientist nowadays needs to know very well is not just how to program, but also how to use the hardware in the best way. And this is kind of the focus of these training events. So to go farther from your knowledge in programming to the knowledge in HPC, so in doing high performance computing. So this change how you do it. So for instance, we said when you go on GPU, you might have to write code with CUDA if you want to run it on NVIDIA GPUs, or with IP if you want to write on AMD GPU. So these are two different programming models that you can use for writing a software that does on GPU. So like I mentioned, once you know the hardware, this will change how you program. There are ways to write it in both languages. I will not say much more, but just to make you understand that it's very important, the knowledge of the architecture. And then there are also all-in-one solution that there are some framework that try to give you tools for writing code for any architecture, which is either CPU, GPU, and in the future you might have to deal also with FPGAs, which are again a completely different programming paradigm. So it's maybe also good to have an understanding on how this all-in-one solution works. So another alternative you can have in producing code that is portable, so that you can use on any hardware, is by referring to what are named as standard libraries. So there are available things, also standard libraries that I don't know if any of you ever heard about BLAS. For instance, BLAS are basic linear algebra subroutines. OLAPACK is another kind of standard library that is linear algebra package. So in these standard libraries, like also MPI is, you're going to have with Yannis tomorrow some look at it. The focus of this standard library is not to provide the code, but to provide a set of functions that then you can use in your code that then are implemented by different hardware providers for their own architecture. So, for instance, BLAS provides you vector-vector operation, matrix-vector operation, matrix-matrix operation. Suppose you want to do a product between two matrices. You can find functions in there. What you have to do is to include the header and use those functions. And then when you are on different hardware, you find libraries compiled for those hardware, like OpenBLAS, Intel MKL, QBLAS that is for NVIDIA GPUs, IPBLAS that is for AMD. that do this operation optimized for the hardware that you use. So this is kind of what you already get for free, almost. For instance, when you do in Python, you use NumPy. The NumPy does these operations, and NumPy is mostly based on this library. In the same way, you can have CuPy that runs on GPUs, and there's the same paradigm. So this is kind of the same concept you would use in Python, but for C or C++. Okay, so moving to the last part of this presentation. So far, we talked about what is high-performance computing from the prospect of a single node. So how to use one of these guys, where you have GPU, CPU, and you need to run your code on it. But we didn't say how you are meant to use our system. So what is the difference between using one node and using the whole system? The major difference, the thing you need to ask yourself, is where the data is. So your data usually is stored in memories, is stored in these guys. And these guys are connected only to your hardware, and they're not visible from other nodes. And often the data that is on your RAM, for instance, it's not visible by the GPU. Indeed, what you have to actually do in your code if you want to use a GPU is to transfer data from your RAM to the VRAM. So there is this issue that the data, it's not shared, so you cannot use simple multi-threading when you need to run on a supercomputer, but you need to think about how to distribute your problem. So the other major topic in HPC is not just how to use optimally a single node, but how to use optimally a whole system. So you want to be able to go from a single node to multi-node program. So, and for doing this, you need to consider distributed computing. And this is what MPI is meant for. MPI is meant for giving you tools to distribute your program along many nodes, send data around, and communicate and do operation with this data. So how are you supposed to distribute the data? Well, there is one way. One way is very simple, task parallelism. So normally if you have a serial program, this will do task 1, task 2, task 3, task 4 in a row. If this task can be done in parallel, okay, very easy. You just need to distribute them and to assign one task per node or per process. So this is something simple, but not very optimal, because what if your task take different amount of time? So suppose the first task take 1 minute, the second task takes half a second, and it's not a good way to parallelize your program, because then it's very difficult to balance the computation between different nodes. So a very normal way that people use, instead of using task parallelism, is to use data parallelism. So data parallelism is what you actually already doing on a GPU, for instance, where you are not processing a big bunch of data serially, but you process in parallel. So you want, instead of processing, let's say an array, the whole thousands of elements to an array, you give hundreds for each process. So this is a better way to parallelize your problem, because the data now are, the tasks are all going to take the same amount of time, because they're going to do the same work, just on different bunch of data. So this is actually the way that most people use to parallelize the problem. There are also some drawbacks. For instance, what if I need information that are stored on another process? So these are all issues that then you need to consider that will affect how you distribute your program. And usually this requires communications. So you need to communicate data from 1 to 3, etc., in order to exchange information. But this is the standard way. There are cases though where data parallelism is not enough. And so what you may want to do is to do a combination of the two and do a kind of pipeline parallelism where you process data and tasks together in a more fancy approach, but this is okay, it's more advanced. And similarly advanced, there is also the way of doing modular computing, and so using at the same time, for instance, CPUs and GPUs. And this is, you may want to do this because there are tasks that performs better on CPU. You can see here that this takes less on CPU than a GPU. Or there are tasks that take less on a GPU with respect to a CPU. So for instance, you want to do what is optimal on each piece of hardware. Again, this is a very advanced topic. What usually you do in a GPU system is to just use the GPU, because the GPU is the one that gives you the power, the computing power. The CPU is just a tool. Okay. This was about parallel computing, and I believe we're almost at the end of the presentation. Yes. Let's try to wrap up and to understand how then you are supposed to do research in HPC. So you, from your point of view, so up to now, I told you about the specification of high performance computing, what you are meant to know. This was kind of general knowledge that one needs to develop further by using these systems. But then every problem is different because it's your problem. So that is, well, then it's the issue of connecting from what is the general the general setup of an HPC system to your problem. So what do you usually have when you need to do research in HPC? Okay, first of all, you have a scientific problem. What this scientific problem has to be? It needs to be a numeric, of course, it needs to require numerical approaches. It needs to be computationally intensive. It's not just a problem that it can run on your laptop. If it runs on your laptop, it's does not require HPC resources, needs to be very intensive. So it's something that most probably you need to scale. So if you have, it still can run on your laptop, but for a size, let's say, 100 of elements, but then maybe your target calculation involves billions of elements. And this is something you cannot do on your laptop because it will take ages. And the only way to solve it is by using one of these systems. And in this way, then it needs to be parallelizable, either via task or data parallelism, like we saw before. So these are all ticks that you should be able to satisfy with your problem. And it's something that then would be good to discuss, talking deeper in with your problem. Looking deeper in what are your requirements. Then you have the software. Of course, you need a piece of software that can run on this system. And most probably it's not the code that you are using on your laptop, because this software needs to be optimized for HPC and needs to be able to be scaled. So needs to be able to run in parallel on multiple nodes. And this is another point that either you already have, or you can look for software that already exists that do your calculation, or you need to produce. Then you need access to one of these systems. That actually is, it's not a too difficult part, but it requires experience as well. Because for getting access, what you need to do is like for getting funding for your research, you need to write a proposal. So you need to there are regular calls for access to computer time. And you need to write a proposal where they ask you to explain your research, the software, how good your software is, runs, etc. So it's better at the beginning to aim to smaller systems where it's easier to get access because there are not many requirements than going directly to the largest. And this is the process also, one of the aim of these training events and also of our center to help you with the process of going from a small system to a large one. So what do you usually need to do for writing a proposal? Well, you can ask very easy for a preparatory access. this is something very simple to do. Usually are a couple of pages. All the system give you preparatory access. They give you some time on the system that you can use to try your code out and collect data. Then you need to test, during this phase, you need to test your software and benchmark it, and write a proposal that is competitive. So your research, both from the scientific and computation point of view, needs to be competitive. Once you get computing time, then you need to produce results. This usually the computing time is for 1 year, and you have 1 year of time to run on this system, produce all your results, collect your statistics, analyze the data, and finally you can write applications on this data. So this is the process that all of us goes through while using HPC resources. I don't know how many of you is familiar with this process. And beside it, what you may want to also consider extra activities that are also very helpful in gaining access to computer time is to perform some numerical research. So you can improve your code from the algorithmic point of view, numerical point of views, develop your software, develop new methodologies. There are also very good points that help you to get access to a system if you show that you are using state-of-the-art technology for doing your calculation. And it's another very focus, another very important focus of your research. First, the left-hand side, then you can consider right-hand side. And clearly this does not, it's not something for one person, usually involves big groups for being able to do this research. And I believe all of you are involved in some, are involved in group research, and so it is a good piece of teamwork that you need to do here. Okay, finally, just some statistics, and we already saw what you guys are interested into. This was the results from a questionnaire that we ran a couple of years ago of the research. And you can understand the research done on this HPC system already in Cyprus, but this, of course, applies worldwide. It's very variegated. So this is why it's difficult also from our side to be able, or actually, the point is that from our side, we are not meant to help you with develop your own software, but to give you the general knowledge that then applied to the various problems can help you to do all the steps that I described before. And you can see that the interests are very varied, from Earth system science, that is the largest, to a good chunk of physics. And yeah, today we heard a lot also about archaeologists that is missing here. And so it's very good that it's expanding. Okay, finally, just a few words about our system. The one you are going to use, we had previously Cythera. This is our legacy supercomputer. Nowadays, the one you are going to use, it's actually Cyclamen, right? Yeah, Yannick, Cyclamen. Yeah, which is a system similar, which is a smaller system, 8 nodes, and it has NVIDIA GPUs with P100s. So this is more a prototype system where that you can use, and we use it in our research. Then there is this Cyclone, that is the system that it's meant for production, and you can get preparatory access by writing an application. And as you can see, it's bigger. It has 16 nodes with 4 NVIDIA GPUs each, and 33 nodes which have only CPU. Okay. This was all from my side and as an introduction. So thank you for your attention, and I believe we have some time for questions. Yeah. So please go ahead.
Okay. Thank you. So the work that you're doing is computational intensive. So my question, I was just wondering, we have to draw a line, for example, how do we know that whatever you're doing is computational intensive? Because we have to look at the running time or the time or the space complexity of whatever you're doing.
Okay, yeah, thank you for your question. So exactly, like I mentioned, your problem needs to be computation intensive, and you understand this by well, by first of all, looking at the amount of data your software is to process, and also kind of at the runtime it takes on your laptop somehow. So these are 2 points that you may wonder about if your problem is computation intensive. So let's say, what is the what kind of problem is it? Is it a problem that can you run it on your laptop or not? Or can you run it on your laptop only on a smaller size? Let's say, I don't know, what is your problem, for instance? Do you have in mind something?
So sometimes back, I was doing some kind of feature importance using machine learning, and
yeah,
I just found normally we just run some feature importance using some basic tools, but I went to research and I found some people working with Chaplay, and I ran the code, but it was not finishing up for 1 hour, so I didn't know that how long it's going to take, so I had to stop it, and okay. I don't know.
But let's talk about machine learning. How is machine learning computation intensive? So all the machine learning problems usually, for instance, use huge data sets that are made of billions of data. And then for learning these data sets, they use maybe very deep neural networks, okay, that require, I don't know, some orders of, I don't know, seconds to get evaluated, okay? So if you have to run, if you're in the case where you have small problems that you need to learn with machine learning, so let's say an image is a relatively small size, but you have billions of them and you want to run the training on them. Usually what in machine learning you do is to run on batch size, so you run on many images together, okay? And if you're in the situation where you have a very big data set to analyze, so you're dealing with big data, then these resources are for you because you can distribute your training, and there are many tools for doing that, where you distribute in different, in this case, GPUs, your batch sizes, and you run the training in parallel. And it can become very computation intensive. So it's not computation intensive from the prospect of evaluating one network, even though it takes some time, but the network is always evaluated on a single image. So the image is a small thing, but you have to run billions of them. And that's why it can become computation intensive. On the other end, you may have to run the network on something that, let's say on a physics systems, which can get very big, can have millions of entries. So let's say you want to run machine learning on a multi-particle system and you want as input the particles. This can become very big, and so what you're scaling is then your network, and you want to parallelize the data. And also that is computation intensive. So there are many directions where your research can become computation intensive and need these resources. Okay. Yeah. Stelios, do you check online if there are questions? Yeah, if there are questions online, okay.
So if there's any questions, please unmute and ask Simone. Otherwise, we will end the session for now, and we will take a break. And I think we start again in
10:30.
10:30. Okay.
11:30.
11:30. Yeah. So yeah, let's take a break, everyone, and meet back here at 11:27. So we start on time. Thanks, guys.
Thank you.